Hi, this is Lab 3. So one of the main goals of this lab was to explore the magnetic field created by a bar magnet and the relationship between distance from the magnet and the magnitude of the created magnetic field. Some of the major physics principles explored in this lab were magnetic fields, Biot-Savart law, and magnetic dipoles. Through the application of the procedures and calculations in this lab, I was able to create a formula for the distance dependence of the magnetic field created around my bar magnet and a computational model of these magnetic fields. Before beginning the lab, first I had to align my phone with the magnetic north pole from the Earth, which was where the x component was equal to 0. Additionally, I had to find where the magnetometer was located within my phone, shown in the illustration below. First, I found the location where the x component of the magnetic field was the highest vertically, and then I found where the location where the y component of the magnetic field was the highest horizontally. The corner where these two lines are is where the magnetometer is located. After all the calibrating, I began the lab by recording 3 distances where the x component of the magnetic field created by the magnet was 1000 microteslas and averaged these distances, giving us R1000. I then recorded and averaged 3 measurements of the x component of the magnetic field when the magnet was placed 1.5 times the distance of R1000 from the phone. I repeated step 2 with distances of 1.75 and 2 times the distance of R1000. After collecting the data, I will use data analysis to determine the mu and the n coefficient of the distance dependence formula. Finally, within GlowScript, I created a model of the bar magnet and its magnetic field at different on and off axis points. So we know that the magnitude of the magnetic field of a bar magnet can be modeled by the magnitude of the magnetic field equal to k times r to the n, where k is a combination of multiple constants and r is the distance between the observation location and the magnet. In this lab, one of our goals was to determine what n is, which we were able to do with the data analysis performed when we model our data linearly with the natural log of the magnitude of the magnetic field equal to the natural log of k plus n times the natural log of r. So when we look at our data, we can see my average R1000 was 0.1083 repeating meters when the x component was 1000 microteslas. And then for 1.5 times R1000, we got an average x component of the magnetic field being about 287 microteslas. For 1.75, we got 147 2/3 microteslas, and for 2, we got 95 and 2/3 microteslas. So down here, we create a table to compare the natural log of the average distance and the natural log of the average x component magnetic field, and we are able to get this nice little linear graph seen here, which matches up with this linear function. So we know that n is equal to negative 3.4007, and ln of k is equal to negative 0.6175. So since we know ln of k is equal to negative 0.6175, k would then be equal to 0.53929. And since we know k is all of the multiple constants, we know that k is equal to mu naught over 4 pi times 2 mu. So we're able to find mu for our computational model, which when moving around the values, we get mu is equal to about 2.696 times 10 to the 6 amps times meter squared. So now looking at this computational model, we see the results here, but we insert all these constants and create the magnet and insert our value for mu. And this function here creates the magnetic field for different locations of R. And this is our scale, and this will be a simulated distance that we can change, which is R. So we have 3 for loops, one for off axis, which finds the magnetic field arrows on places that are perpendicular to the magnet, and then points that are on the magnet's dipole moment axis. And then down here, I created another for loop to calculate the 45-degree axis of the magnetic field from the magnet. So when we run the program, we see what we expect, where along the axis, the magnetic field moves with the magnet, and then as it goes around, it starts pointing out and then in on this side for the 45 degrees, and then it comes back around moving opposite of the dipole moment whenever we're perpendicular to the axis, which is also the smallest magnitude, and comes back in. So this is the correct magnitude we expect. And from here, we can see that for the 45-degree axis, we get about 47.659 and 142.977. This compares similarly to our observed values of roughly 65 and 160, and this helps support that my computational model is accurate. So some of the questions posed is, what if we hadn't oriented our experiment to compensate for the magnetic north, and instead laid it out at some intermediate angle with respect to the Earth's magnetic field? My results would have varied completely, since the Earth's magnetic field would have had a large impact on the different components of B. This difference would be in the order of the magnetic field of Earth times the tangent of whatever angle we are off of the north axis. Now, what if we were to stick two identical magnets together end to end? How would you expect my measurements to differ? The direction of the magnetic field at all the locations relative to the new double bar magnet would be the same, but the magnitude would have increased 2 times due to the magnetic dipole moment increasing. Through the use of data analysis and computational models, I was able to determine many different values and models of the magnetic field of a bar magnet. I found the value of N to be negative 3.4007, mu as 2.696 times 10 to the 6, and saw that my magnetic field vectors for observed and experimental 45-degree axis to be roughly equal. Thank you.